All right, thank you for joining us here. Hopefully in class you were able to kind of draw this little cart on an inclined plane and start to label the force diagram for that. But essentially what I want you to try to understand is the relationship between this angle of incline and the coefficient of friction. So here what we're going to do in just a moment is we are going to watch me lift up this ramp, lift it, lift it, lift it. Now when it's not moving, when this block is, this cart, this sled, whatever you want to call it, when it is not moving, we say forces are balanced. But once it starts to slide, once it starts to move, we say the forces become unbalanced. So here we go. It's balanced, balanced, balanced. There it starts to move. Now, forces become unbalanced. On a simple level, it's the weight. The way I kind of think of it, it's when the weight overcomes that force due to friction, the cart starts to move. So here's what all these little story problems are trying to design to get you to think about. There's angles where it doesn't move, but then there's also going to be an angle where it does start to move. It does start to slide down the ramp. So that's really the little kind of scenario that these story problems are trying to get you to think about. And this whole thing is based on trying to understand the drawing. So on this drawing, here's our cart. It's going to slide down our ramp. Our angle of incline is this angle theta. There's a force due to friction holding it there. There's the weight. Now we still draw the weight vector straight down, the force due to gravity. I'm trying, this normal force here is supposed to be perpendicular to the ramp. There's a 90-degree angle between the frictional force and the normal force. In fact, remember, normal forces, we say, or even in math, a normal line is perpendicular to the plane. All right, so I'm hoping you can kind of make sense of this little force diagram. And then the new thing here is we're essentially tilting our x and y axis. Or some people actually just had some classes, some students just tilt their paper, kind of tilt your paper a little bit. But the thing is we want our x-axis to line up with the incline, with the ramp, with the surface. And we want our y-axis to be perpendicular to that surface. So just tilting our x and y axis, this angle of theta, what that allows us to do is when I draw there's a component to its weight that lines up along the y-axis. And there's a component of its weight, the force due to gravity, that lines up along this tilted x-axis. It's the FGX that balances the frictional force when it's not moving. And it's the FGY that balances the normal force when it's not moving. Now, so when you look at that, if FGY is normal force, and FGX is frictional force, this ratio of frictional force, the ratio of frictional force to normal force matches the ratio of FGX to FGY. So in other words, mu, our coefficient of friction, is that. Now if you look at this little picture, I think you can see how our angle of incline on the ramp, it is equal to this angle inside our little triangle that we drew. I don't know, it gets a little messy and maybe in the way I sketched it out here. But kind of the way I think of it is, if this is theta here, hopefully you can kind of recognize that this angle here would also be theta. Now remember, this is our normal force. This is supposed to be the ramp. So this angle that's left over here, like I said, I didn't draw it perfectly, but there should have been a 90-degree angle between the ramp and the normal force. So this angle left over here is 90 minus theta. That would also be equal then to this angle. Now if you kind of look at it, so here, there's a 90-degree angle here. So this is theta, everything that's left over. I guess kind of the way I looked at it too, this is a 90-degree angle here. So this 90-degree angle there, if this is 90 minus, then this angle here is theta. I don't know, there's a few ways to kind of make sense of the geometry, and that really wasn't the purpose of this. But this, on a simple level, this angle of incline equal this angle theta in our triangle. So the shortcut we can use on these problems is to recognize that our coefficient of friction, our mu value, would equal the opposite, FGX, over the adjacent, FGY. So opposite over adjacent is tangent. So the shortcut, and what kind of helps us go through, and there's a lot of repetition in these problems, but what helps us go through that is if I don't give you the coefficient of friction, you can figure it out because mu will equal the tangent theta, and theta is our angle of incline. All right, so if we look at a question like this, determine the value of mu. Well, I got my angle of incline at 25 degrees. My angle's 25 degrees. Take the tangent of that, and that does equal mu, our coefficient of friction. Kind of looking at the next question. Now, I stacked up some different amount of weight in there, but what's kind of interesting to me is if the angle's the same, then your mu is the same. So once again, we can kind of use that shortcut. If you know your angle of incline, you know this angle in our little force diagram, so you know this ratio of FGX to FGY. Remember, if it's balanced, FGX equals force friction. If it's balanced, FGY equals the normal force. Okay. Now, the other thing, and I think you can kind of see this by just playing with those ramps a little bit, if the incline gets smaller, so here it's a 15-degree angle. If the incline is smaller, your mu value, your coefficient, is smaller. In other words, I didn't have to tilt the ramp as much to make it move because it was more slippery. So on these problems here, they're just like all of our other sliding block problems, especially when you just tilt our axis here. But the new thing is that if I give you this angle of incline, you should hopefully be able to find the value of mu, find that coefficient of friction. So here, looking at number 4, if it's a steeper incline to make it move, there's a bigger coefficient of friction. And really just kind of more the same here on number 5. On this one, I give you the mu, ask you for the angle. So you just take the inverse tangent would give you the angle. Same kind of idea here. Looking at number 6, there's a different mu value. I kind of just like that comparison. So there's more, it's a stickier surface, which would mean you'd have to lift it more to make it move. And in fact, I do recognize that there's a bigger angle of incline there. Moving on, number 7. Now this is where it gets a little different. Now this is where it actually turns into a problem. Okay, so it's not balanced. The block is going to move. All right, the block is going to start accelerating. So when it starts accelerating, now once again, this kind of just becomes a lot like those challenge problems or some of those other sliding block problems we were looking at. So here's the force diagram we'll use. We'll still kind of like any sliding block, any force diagram problem. Label your forces, figure out what happens to it. So our steps to solve, we'll figure out our force due to gravity. We'll use our triangle to figure out those components, the x and y components of our force due to gravity. It's easy to find that normal force because it's going to balance. If you found FGY, you know normal force. Now, the frictional force won't balance if it's moving, so we'll have to find the frictional force. But if we know mu and we know normal force, it should be easy to find the frictional force. Once you know the frictional force, you should hopefully look at the fact that the weight, that x component of its weight should be bigger than friction if it moves. And that's what allows you to figure out how it's accelerating. Okay, so let's take a peek here. Let's see here. So number 7 again, here we are. So first step, get the weight. A 5 kilogram block weighs 50 newtons. Given that triangle, all right, so here's my triangle. So the opposite over, so that the weight is your hypotenuse. I don't know if you see that in the way this triangle is drawn. That 50 newtons is your hypotenuse. So step 2, we can use sine would be opposite over hypotenuse. That gives us FGX. Adjacent over hypotenuse gives us FGY. So once we've labeled those, the FGY, step 3, the FGY is the same as our normal force. Once you got the normal force, multiply it by our coefficient of friction, which was just given there. That will give you the force of friction. Now that should, remember the weight, if it is moving, the x component of its weight is 21 newtons, should be enough to overcome friction. And certainly at 21 would pull harder than that. So I just subtract, that's how you find the net or sum force. Subtract to get your net force in the direction of motion. Divide that by the mass, and you got its acceleration. Yeah, here's another one. Now, the thing that I think was kind of interesting here, for me at least, is even though I'm stacking up more weight, and it's going to weigh more, if you have the same angle and you have the same amount of friction, that cart is going to accelerate the same way. You can go through all these steps. So we got 80 newtons. We have 33, 34 of those newtons pulling down the ramp. We got 72 of those newtons balancing the normal force. So then when you go over here, so we got our frictional force to be 14 by multiplying mu and no. So it's different numbers. But once again, this force here should overcome our frictional force. And when you do the algebra, do the math, it's interesting that it does accelerate in the same manner. So if you did get a chance to kind of play around, it's really not much. You just lift up the cart and watch it slide. What's interesting is the amount of weight you stack in that sled doesn't change when it slides, doesn't change its acceleration either. So yeah, really kind of more the same here on number 9. Draw a little picture, find the weight, step 1, where's that? Find the weight. Draw a triangle, find the x and y components of the weight. Find the normal force, which balances the y component of the weight. Find friction. If it's moving, the x component should overcome friction. And then you'll just figure out, divide that net force by the mass, and that will tell you how it accelerates. Number 10, once again, kind of more the same. Given a mu, given an angle, given a mass, how is this stuff going to move? Step 1, find the weight. Step 2, draw your triangle. Step 3, balance or figure out that normal force. It's equal to the y component. Figure out your frictional force. There should be enough x, enough of its weight to overcome friction. So 16 does overcome, or no, I'm sorry, 29 does overcome the force due to friction. Those forces sum together, divide it by the mass, and that will give you how it accelerates. Here's another one, kind of more the same. It is kind of very repetitive. Now the thing with this one, I don't know if you noticed, same angle, same coefficient of friction. it's going to accelerate the same. To me, it is kind of interesting that you can change the mass, go through all the steps, and you'll arrive at the same acceleration. I hope that helped a little bit, but really, so for the quiz, the steps you want to follow are draw your picture, find your weight, step 1, draw your triangle, step 2, figure out the normal force, balances the FGY, step 3, find the frictional force, step 4, subtract that frictional force from the component of its weight that pulls it down, divide it by the mass, and you'll have your value for acceleration. I don't know if that helped, but once again, it's open notes. Use our website. Thanks for all your attention.